Okay, hi guys. So we'll be continuing on seeing more on van der Waals equation of real gases. So this is the van der Waals equation. So if you just look at it, it is P plus an square upon V square multiplied with V minus NB equals nRT. And if you look at this second bracket term, so this is the effective volume, which is means rather this is we are subtracting the volume of the vessel from the effective volume occupied by the n moles of gas. So this actually represents the actual space which is available for the molecules to roam around in the vessel. Okay, and so here we actually represent B with excluded volume or co-volume, or the effective volume occupied by 1 mole of real gas, and this is nothing but 4 multiplied by volume of 1 mole of gas. So we'll be looking into the derivation of the same. So suppose we had the interaction between these two molecules, and these two molecules have a radii of r, so the center to center distance between these two molecules would be 2r. So the excluded volume per pair of molecules would be, so as the radii of the two molecules is 2r, hence it would be half of, rather we'll come to this half term later, the excluded volume would be 4 by 3 pi 2r cube, and this half is introduced because we are considering excluded volume per pair of molecules. So the total excluded volume would be per total excluded volume would be total excluded volume per molecule would be half of this, because this is per pair of molecules. Okay, so from this is the excluded volume per molecule. Okay, so which is nothing but 4 into 4 by 3 into pi r cube, and now we are interested in the excluded volume per mole of gas. So excluded volume per mole of gas is nothing but B. So B would be just multiplying this into Avogadro number, which would be 4 into 4 by 3 pi r cube multiplied with Avogadro number. Okay, so this is the excluded volume per mole of gas, or the value of B. Now let's actually see the pressure correction term, which was used in the van der Waals equation, which was P plus an square upon B square upon V square rather. So pressure correction term which was used there was an square upon V square. So we would look how it is getting derived here. So suppose let's consider a vessel. Okay, so in this vessel we have some gas molecules. Okay, so van der Waals actually considered intermolecular attraction between gas molecules. Attraction between gas molecules. Okay, so what do you mean by this? This actually means that whenever there is a gas molecule, there are many molecules which are attracting this gas molecule towards themselves. Okay, and suppose this gas molecule was at the edge of the vessel. Okay, so no attractive forces would come from this side of the vessel. Why? Because there is no existent gas molecule on this side of the vessel. Hence, for the molecules which are on the edge of the vessel would be attracted by all the gas molecules from one side. Okay, and if we take a look at this gas molecule supposedly, so this gas molecule is been attracted evenly from all the sides. So we can say that the pressure or force which is felt by a molecule would be some quantity, some positive quantity for a molecule which is nearer to the edge of the vessel, and for a molecule which is comparatively into the center of the vessel would have felt zero attractive forces, simply because it has been attracted from all the sides by different adjacent gas molecules. Okay, so we can write that net intermolecular attraction between gas molecules present nearly at the center of the vessel would be 0. So net intermolecular attraction between molecules present in nearly center of the vessel would be 0. Okay, but this pressure which is felt, or this force which is felt by the molecules which are nearer to the edge of the vessel, would have to be considered, and rather this term has to be added to the P which was originally there on the vessel to have a complete or a realistic view of the total pressure which is existent inside the vessel. Okay, so we have to introduce some pressure correction term for that to include these pressures which is actually felt by the gas molecules present in the vessel apart from the originally existing pressure. So pressure correction term have to be added. So this term would actually be depending on, we can say that first, number of molecules per unit volume. Okay, and this term would also be dependent on number of collisions striking on the wall of vessel per unit time. Okay, so what is the number of molecules per unit volume? Number of molecules per unit volume would be nothing but n upon v of the vessel. Okay, and what would be the number of collisions striking on the wall of the vessel per unit time? So we already have the total number of molecules and the volume of the vessel. So what would be the total number of collisions striking on the wall? So total number of collisions striking on the wall would be proportional to number of molecules divided by v. Okay, because that's how we represent how many molecules are there which would be attacking per unit volume, or in other words we can say that collisions striking on the wall would be proportional to number of molecules per unit volume of the vessel as well. Okay, so this is just a common sense thing which we are using here. So again, number of collisions per unit time would also be dependent on number of molecules and volume of the vessel. So just an analogy here, that higher the number of molecules, more would be the collision rate. Okay, and lower the volume, again more would be the collision of molecules on the walls of the vessel. Okay, so with the same analogy we write it n by v. Okay, so let me erase it because it was just used for the explanation sake. Okay, so now what we have is, we saw that number of molecules per unit volume is n by v, and number of collisions would also be directly proportional to n and inversely proportional to volume. So we can write that pressure correction term is indeed proportional to n square by v square. By removing the proportionality sign, we can actually introduce a gas constant here, which would be a. So pressure correction term would be a n square upon v square. Okay, and if we have to discuss the units of a and b, so units of a would be atm pressure square upon mole square. Atm rather liter square by mole square. Or rather, let me again write it. Okay, and for B it would be liter per mole. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing on physical significance of A and B, and then we'll be talking about compressibility factors. So till then, good luck and goodbye.